Hi, welcome to Algebra 2 Common Core. Tonight we're going to take a look at polynomial identities. So to begin with, the definition of an identity, please fill this into the box in your notes. An identity is an expression that is always true. So regardless of what x values or what input numbers we use, the expression is always true. So the left side of the equation has to equal the right side of the equation all the time. Here are some identities that we are familiar with. The first one, x squared minus y squared. We should recognize that as the difference of two perfect squares. So we can rewrite x squared minus y squared as x plus y times x minus y. No matter what values we use for x and y, when I square x and subtract y squared, I will always get the answer x plus y times x minus y. Likewise, we know the identities for the sum and difference of two cubes. So let's start with the difference of two cubes. Remember that the first factor is going to be x minus y, and then we make that pattern where we square that first term. So x gets squared. We multiply the two pieces together but change the sign. So that's going to be a plus xy. And then, of course, we square this term right here, so that's going to be plus y squared. So we learned this pattern back a few chapters ago when we were learning factoring of the difference of two cubes. The sum of two cubes is very similar. So x cubed plus y cubed is going to be x plus y times x squared minus xy plus y squared. So these three are examples of identities that no matter what values we substitute for x and y, the left side of the equation will match the right side of the equation. Always, always, always. Let's try example number 1 where it says, let's verify that this x plus a squared minus x minus a squared is equal to 4ax. So when I see that word verify, it means let's show that the left side is equal to the right side. So we have to perform the algebra that's required here. I'm going to go off to the side and say, okay, I've got to multiply x plus a times x plus a. So one way of doing it is using my box. So x times x gives me x squared. A times x gives me ax. X times a also gives me ax. I'm going to write it in the same way so that I can see that they're like terms. A times a squared. So the first binomial squared is giving me x squared plus 2ax plus a squared. Now let's look at the second binomial and square that. So I'm going to come over here and make a box for that one as well. So I'll have x minus a times x minus a. Multiplying, I'm getting x squared minus ax plus a squared. Now be very careful in this part. I've got to subtract that whole polynomial. So I'm going to say let's subtract x squared minus 2ax plus a squared. And I want to know, does the result always equal 4 times a times x? So putting together like terms, I'm going to first of all distribute the minus sign. So x squared plus 2ax plus a squared minus x squared plus 2ax minus a squared. Does that equal 4ax? Now, of course, I have some like terms. My x squared subtracts x squared. A squared subtracts a squared. So that allows me to add together the only terms that are left on the left side. 4ax is equal to 4ax. So this is how I verify that an identity is true, by showing that the left side is always equal to the right side. and I've shown this algebraically. In this lesson, we're going to see that sometimes identities are very helpful tools in order to help us to do mental math quickly. So let's demonstrate when we see the identity x squared minus y squared is equal to x minus y times x plus y. So that's the identity that we are focusing on in this example. Test this identity with the pair x equals 10, y equals 3. So on both the left and right side of the equation, I'm going to substitute 10 for x, so I've got 10 squared, 3 for y, so I've got minus 3 squared, and I want to know, does this equal 10 minus 3 times 10 plus 3? So 10 squared we of course know is 100, 3 squared we know is 9, 100 minus 9 is of course 91. Now go to the right side of the equation. 10 minus 3, that's 7. 10 plus 3, that's 13. 7 times 13 is also 91. So clearly this works for specifically the pair x equals 10 and y equals 3. So that just gives an overlook of when we have just one set of values, does the identity work? That's not enough to prove that this is an identity. In order to prove that we have an identity, we want to show that it works for all x and y. So that means use your identity equation, x squared minus y squared, and show that when I multiply x minus y times x plus y, I get exactly what I have on the left side. So doing either double distribution or making your box, I see that I'm getting x squared plus xy minus xy minus y squared. Putting together my like terms, the xy and the negative xy cancel. So I'm getting x squared minus y squared is equal to x squared minus y squared. So clearly, this is an identity because the left side and the right side match. In part C, let's use this identity to evaluate the difference of 50 squared minus 49 squared without my calculator. I'm going to go back to what the identity is. X squared minus y squared is equal to x minus y times x plus y. So I'm substituting 50 for x, 49 for y. So you'll notice that this would be quite a calculation to do in our head without a graphing calculator. But if we think that every time we see x, we're going to use 50, and every time we see y, we're going to use 49, we have 50 minus 49 times 50 plus 49. So we're using the identity that we've just proven to calculate this answer. 50 minus 49 is 1. 50 plus 49 is 99. 1 times 99 is 99. So if we were to do this calculation on our calculator, 50 squared minus 49 squared, we would get 99. Now, of course, we've used a different calculation to get to that point. Let's look at it in a slightly different way. If I now have 51 times 49, then I'm going to use the 51 as the x plus y. I'm going to use the 49 as the x minus y. So you'll notice that in this situation, x is equal to 50, y is equal to 1. So let's go back to our identity. X plus y times x minus y has to equal x squared minus y squared. So 50 plus 1 times 50 minus 1, which of course is 51 times 49, would have to equal 50 squared minus 1 squared. Now that's a calculation that we can handle in our head. 50 squared, 5 squared is 25, but then I'm going to add 2 zeros because of the 50 being squared, minus 1. So this calculation would just give me 2,499. Again, you can see that this calculation is very doable in our head when we've rewritten it using the identity. In example 3, we want to prove the identity that a plus b squared is equal to a squared plus 2ab plus b squared. So that's no different than just multiplying together a plus b times a plus b. So doing my box multiplication, I've got a squared, ab, and b squared. So I can clearly see that a squared plus 2ab plus b squared is equal to exactly the same thing on the right side of the equation. So yes, this is an identity because I have algebraically shown that the left side and the right side are equal to each other. Now, if I want to solve for 35 squared, then I'm just going to say that where I see a, I'm going to put 30. Where I see b, I'm going to put 5. Now there's nothing special about the numbers 30 and 5 other than the fact that they add to 35. Could I have used 20 and 15? Could I have used 10 and 25? Yes, I could have used any of those, but whichever ones I've used, I do have to know what their square is. So every place that I see an a, I'm going to put a 30. So 30 squared plus 2 times 30 times 5 plus 5 squared. So this is 35 squared using this identity. 30 squared is 900. 2 times 30 times 5 just means 30 multiplied by 10, 300, plus 25, giving us a final answer of 1225. You could check that on your calculator. In the next example, we're going to see how identities can be applied to things like right triangles. We all know that the legs of a right triangle have to follow the Pythagorean theorem. So therefore, we're going to say that a squared plus b squared equals c squared, according to the Pythagorean theorem. Now the a and the b just stand for the two legs, and the c, of course, is the hypotenuse. So the question says, let's show that 2x, which is the first leg, squared, plus the second leg squared, x squared minus 1 squared, is equal to x squared plus 1 squared, which is just the hypotenuse. So let's go through and square. 2x, when I square that, that's a monomial, so that's giving me 4x squared. When I square this binomial, x squared minus 1, it's giving me x to the fourth, follow the pattern that we've been using all year, twice the product of the two terms in the binomial, so that's going to be a minus 2x squared, plus the last term squared, so plus 1. Combining like terms on the left side, I've got x to the fourth plus 2x squared plus 1. On the right side, squaring this binomial, I'm getting x to the fourth plus 2x squared plus 1. So you'll notice that the left side of the equation and the right side of the equation match exactly. So when they match exactly, that tells me that I've got an identity that works. And this just verifies that these terms can be used to represent the sides of a right triangle. In example number 5, this happens to be a question that was on the Regents exam just this past June. It says, let's algebraically prove this expression, this equation actually. Now, don't be thrown off by the part that says where x does not equal negative 2. All this means is I can't use negative 2. Negative 2 is not in the domain of this equation. I'm not going to do anything with the negative 2. Instead, I'm going to show that the left side is equal to the right side. Well, we just finished our section on rational expressions, where we said that whenever we are adding two rational expressions together, we have to find the least common denominator. This one's pretty easy. It's going to be x cubed plus 8. So that just means that I've got to take that middle term. So the left side already has the x cubed plus 8, so I'm going to leave that alone. On the right side, the 1 doesn't have an x cubed plus 8, so I'm going to multiply the numerator and denominator by x cubed plus 8. Second fraction already has that common denominator, so it's going to look like this. Go ahead and multiply on the right side, so I'm getting x cubed plus 8 over x cubed plus 8. Adding on 1 over x cubed plus 8, I do get x cubed plus 9 over x cubed plus 8. And that's exactly what I wanted to have, x cubed plus 9 over x cubed plus 8. Left side matches the right side, so I've proven this identity. So again, to prove algebraically, I have to show that the left side is equal to the right side for all values of x. Example number 6 also came from a past Common Core Regents exam. It says which factorization is incorrect. So we're looking for the one that is not an identity. So I'm going to go through these kind of quickly. Number 1 we can see is just our difference of two perfect squares. So that does factor into 2k plus 7 times 2k minus 7. This is definitely a true identity. Number 2. Did you recognize that as the difference of two cubes? So you'll notice that the first factor is a minus 2b, and the second factor, we take this term and square it, so that's a squared. We multiply our two terms together and change the sign, so that's plus 2ab, and then we square the second term, so that's plus 4b squared. So once again, I have a true identity. So it's really going to be just our work in identifying number 3 and number 4. So starting with number 3, I can see that on the left side, I have the polynomial written in standard form, and on the right side, it's in factored form. I think it's probably, well, I guess I could go either direction. I could either say, let's multiply this out and see if it's equal to this, or could I factor this one and see if it's equal to this. I'm thinking I might go with the multiplication step here. So I'm going to say let's take m minus 2 and multiply by m minus 2 first of all. That's giving me m squared minus 2m, which is minus 4m, plus 4. But now I need to multiply that trinomial, m squared minus 4m plus 4 times the last binomial, m plus 3. So going ahead with the multiplication, I've got m cubed minus 4m squared, 4m, 3m squared minus 12m plus 12. So this product gives us m to the third minus m squared minus 8m plus 12. And clearly I see that this does not match, so this is looking like a false statement. Let's just check number 4 before assuming that number 3 is the incorrect one. I'm going to do it the same way. Let's multiply these two together. So that's going to give me t squared plus 3t plus 2 multiplied by t plus 3. I'm again going to set up my box to multiply a trinomial times a binomial. So t squared, 3t, and 2, t plus 3. I'm getting t cubed, 3t squared, 2t, 3t squared, 9t, and 6. So that whole product is t cubed plus 6t squared plus 11t plus 6. Now for this one, you'll notice that I've got like terms in my original left side. So when I add on the left side, I'm getting t to the third. These two add together to be 6t squared. These two add together to give me 11t. And then I have a plus 6. So I of course see that the left side and the right side match. So number 4 is also true. So number 3 is the only factorization that is incorrect. Let's do example 7 together, and then I'm going to see if you can try example number 8 based on what we do on number 7. We've got some information. A squared plus b squared is 4. A minus b squared is 2. And we want to find the value of a times b. So this looks very much like an identity that we've been working with quite a bit tonight. So let's take our a minus b squared and let's rewrite that in multiplied form. So of course that's going to give us a squared minus 2ab plus b squared. Now I know that I was given a squared plus b squared. So it would be helpful if I rewrite the right side and just use the commutative property to rearrange terms and say a squared plus b squared minus 2ab. That's still equal to a minus b squared. It's just written in a different order. Now I have some of these answers. A minus b squared, that's 2. On the right side, a squared plus b squared, that's 4. And I still have negative 2ab. I specifically want to solve for ab. So let's get our terms together. So subtracting 4 from both sides of the equation, I have negative 2 equals negative 2ab. Now I'm not trying to solve for a, I'm not trying to solve for b, I'm trying to find the value of a times b. So to get that value, I'm just going to divide both sides of the equation by negative 2, and that tells me then that the product AB must equal 1. And again, you'll notice that we never found the value for A and the value for B. We just wanted the value of the product A times B. Now take a few minutes and see what you can do with exercise number 8. I want you really to give it a try before you come back and check your answers. I got as my solution 175. You can see that I set this up as a squared minus b squared, which is the identity a squared minus b squared equals a plus b times a minus b. Well, our givens were actually just those factors on the right side. So I replaced a minus b with 17.5. I replaced a plus b with 10. Again, it was not necessary to know the values of a and b. I just knew the relationship a plus b and a minus b. Multiplying these together gave me 175, and that's exactly what I was looking for, the difference between the two squares. Well, have a great night, and we'll work some more in class on our polynomial identities. See you next time. Bye-bye.